we can check during the break or something. Okay, so last time we talked about parametric curves. Let's remind ourselves how this works. So it's very convenient, you can just scroll back to the previous lecture. So the necessity to introduce parametric curves was to so that we can describe functions. So we can describe curves which cannot be given by a function of a single variable. So for now we are talking about curves in 2 dimensions on a plane. So in this plot, the purple curve can be given by a continuous function of one variable. However, the orange curve cannot, right? So, so first of all, if you try to describe it in terms of a function of one variable, you're going to have to use multivariate function. So because for some values of x, there are more than one value of the function, which typically we don't consider in real analysis, but nevertheless. And second of all, we can have this self-intersection points like here, right? So again, it's sort of because of those multivariateness and because of the self-intersection points, we need to find a new tool to describe it, and that's where the parametric curves, parametric equations come to rescue. So we have a instead of having a single function y in terms of x or x in terms of y, we give a pair of functions x. So we introduce a new parameter t, which varies between 2 limits. So it's convenient to think of t as time elapsed from the beginning of the experiment to the end, and then you just trace in the coordinates of the particle in the xy plane, right? So at every time t, right? So this particle is located at point x of t, comma y of t, right? It's a unique address, unique position of that point in the coordinate plane, and as t changes, this point moves. Well, actually, you know, it doesn't have to move, right? So, for example, you can give an equation when just you know, there's this sort of bit ridiculous example, but nevertheless, if you just say that x is a constant and y is a constant, some other constant, let me call it no, x is equal to c1 and y is equal to c2. So they do not depend on t at all, right? So, and this is still a curve, right? It's a very boring curve with just one point with coordinates c1 and c2. But nevertheless, it fits the definition. Yeah. So this curve is not differentiable in the sense which curves are differentiable. So this is so-called well, it's like a degenerate point, right? So in this point, curves are not differentiable. So, but otherwise, as you vary this parameter t, you will move along the curve, and then, for example, so and this way you don't really care if you have this problems with multivariateness. If you have points where the derivative would be infinite, it's really not important. So we'll talk about this in a moment when we talk about tangents, but at least to describe the position of the point, there is no problem. Now, when you talk about self-intersections, this is interesting here. So although this point here is passed by the curve twice, it happens at different moments in time, at different values of t, right? So say we approach this point from here. So we got to this point, and then so this point is x of t1, comma y of t2, y of t1, right? And then we made the loop, so the parameter t changed even further, and came back again to this point. And this point has also a different description in terms of x of t2, comma y of t2, right? So although this is the same point in terms of on the xy plane, technically we should think of 2 different points which parameterize the curve, right? So think of it the following way. So let's say there's a plane where we draw this curve, and then we add the third direction, vertical direction, which is time. And then, of course, as time evolves, the curve will spiral up, right? And then these 2 points will be separated in time. So this is another way to look at this. It's absolutely natural. It's not absolutely natural way to do. So some of you asked me last time about 4-dimensional space, and indeed, so there is such a thing in physics. Is this where the fourth directions will have three special dimensions, x, y, and z, and the fourth direction is time. Although it's not literally Euclidean 4-dimensional space, it's rather 4-dimensional Minkowski space. Like the way time direction works is it's not on equal footing with all other directions. Like the distance, when you measure distances, we'll talk about it later. So when you measure distances, the changes in time direction, they are counted differently than changes in spatial direction. For example, the interval, the distance between 2 points in space-time, when you calculate the square of the distance, there will be a minus sign in front of the square of the time interval. Space-time, yes, it's called space-time. Yeah. Any questions about this? Okay, good. Right, and then we looked at a bunch of examples, and then there will be yet more examples in the homework. So, yeah, and then we looked at the circles and the ellipses. We'll return to ellipses a bit later when we do conical sections, right? And towards the end, we did those curves when the periods made sort of the ratio. Well, I call it period, but yeah, anyway, just for example, if you say that fx of t is equal to cosine omega t, right? So here you can just sort of the period. It's a time that takes for the point to make a full revolution will be 2 pi divided by omega, right? So you can check that here. So when t is equal to 0, cosine is equal to 1. So this argument is equal to 0. When t is equal to the period, the argument changes by 2 pi. Right? So, so for example, here when you have here we have 1, here we have 2, right? So the period of the first function of this x function is twice bigger, right, than the period of the y function. Okay. Nobody figure out the answer for the problem? For those who are just joining us, again, it's a fun problem. You ask to evaluate, well, integral dx over dx. Infinity. I'm still confused about what w represents. Oh, like this omega here, right? So so say you have a function x of t equals cosine omega t, right? Where omega is some number, some real number, right? So let's draw. Okay, let's talk about it, right? If you haven't seen it before, although we don't really need it now, but nevertheless. So let's draw several plots, right? Let's take a cosine function, and then we'll take a cosine, but which looks like this. Okay. Then the purple curve says cosine of. Well, so here's a question to Sharon, right? So here's or to anybody, in fact, right? So say there's cosine omega 1 t. It's the purple curve, and then the orange curve will be cosine of omega 2 t. Right? Question: who's bigger, omega 1 or omega 2? Which sign should I put between them? So one oscillates slowly, the other oscillates quickly. So omega 2 is, right, so indeed, so the sign should be less, right? Simply because, well, it takes, we can just count, right? So so this is the point where the first one completes completes the period, right? We start from 1 and then we come back to 1. Whereas the second curve, it takes less time, right? So right here, so we can call this interval T1 and maybe T2. T2 and this interval T1. So omega 1 is less than omega 2 and T1 is bigger than T2. So a period is inversely proportional to omega, and omega is called frequency. Frequency of oscillations. So the frequency which is measured in hertz is the omega divided by 2 pi. Like there is no 2 pi here. So sort of the Does that answer your question, Sharon? Good. Okay. Okay, let's leave it for later. Okay, now let's talk about tangent lines. Next topic. So, quick reminder from single variable calculus how the tangents work. So let's say we have a plot of a graph, right? And then we're studying the behavior of the function around some point here with coordinates x0, y0, right? And then, well, you can take other point here. Well, the way I drew it, it's not really distinguishable from the line. So we can try to do a slightly better job with the plot. So let's say that's something, it bends like this maybe, right? And well, let's do it here. So then you can take a point with coordinates y and x, and then connect these 2 points with a straight line, with a that's a bummer. Somehow my editor, okay, sorry, give me a second. Otherwise I can just do a new one in a different place. You know what? Let me just redo it. All right, so we have 2 points with coordinates y0 and y, and x0 and x, and then we'll connect these 2 points with a straight line, right? And we'll try to we'll take the limit as x approaches x0, right? And therefore, so Fad is asking, can I please write the name of the lesson and if possible the section on the top, which class will begin? Sure. So right now we are in section 10.2. So today we'll be talking about sections 10.2 and a little bit of 10.1 and 10.3. Yeah, sure. So, okay. Yeah, I think it probably makes sense for, okay, we can put it here. Lecture number 2. And here it will be section 10.1 through 10.3. Yeah, and then the first lecture was just the introduction. How the quiz is going to work for those in the 12.2 lecture. So, right, so there is no 12, right, so 12.2 is just the, as I explained to many of you in the email, the 12.2 is just the kind of the, what is it, like assigned time for the class, but we have in one lecture per day. So the quizzes will be, so by default, quizzes will be during that time. So if you assign to the 12.2 lecture, you will be taking quiz during that time. If due to the time difference or wherever you cannot do this, you should notify me before the quiz. So I'll make an announcement just before the quiz, and we'll arrange the special time for you. So the quizzes will be made in terms of assignments on B courses. So at a given time, I'll upload the quiz, the file, the PDF, and you can either, if you're using a tablet like iPad or anything else, that you can just annotate on top of it. If not, you can just write it on a sheet of paper and then scan it or take pictures and upload to B courses. Well, yeah, so, right, I mean, I think the answer to, so Hannah Liu is asking, can we use a calculator for the quiz? Well, I mean, I think the answer will be yes, but what I'll be looking for is, so you can use it to check your answer. So when you're solving the problem, you'll need to show me all the steps of the calculation. So of course you are free, since it's a take-home quiz, nothing stops you from checking your answer on the computer or using Mathematica or Wolfram Alpha or calculator, but simply obtaining the correct answer will not give you a full point, or will not give you a point. Just to confirm, they are intended to be completed in the class timing. Yes, yes. So even less than that. So a quiz will be 1 hour. So our lecture is technically 2 hours. The quiz is it will be 1 hour thing. The midterm will be 2 hours. So quiz 1 hour, midterm 2 hours, and final 3 hours. Yeah. Okay. So but the first quiz will not come until next week. Yeah, so and what we're doing here, we are, as x approaches x0, we can see that the red line, this straight line, becomes closer and closer, approaches closer and closer to the graph, to the purple graph here, and then if you zoom in really close, they become almost indistinguishable, right? And so this is the notion of the tangent line. So the tangent line to the graph of the function y equals f of x at point x0, right, is a line which almost coincides with the graph at that point, right? And the way it's done is using the limit. So as x approaches x0, f of x approaches f of x0, right? And this red tangent line. So before we take the limit, right? We can write down the equation for the tangent line. There's a slope here, right? So the slope is the difference between, is the ratio of of this segment over this one, right? So slope is f of x minus f of x0 divided by x minus x0. Then if you take the limit as x goes to x0, this becomes the derivative of the function at x0, right? So the slope or the tangent of this angle alpha at x equals x0 is equal to the derivative, the value of the derivative of the function at that point, right? And then we know that this function passes, the line passes through the point x0, y0. So we can say that any point on this line, let's say this point here, satisfies the following equation, right? So that y is equal to f prime. Well, basically we can just use this we can just use this equation, right? So in fact we can use the right. So yeah, so we have x prime of x minus x0 plus f of x0 or y0. Right, so this is the equation. This is the equation for the tangent line, right? So you can check here that when x is equal to x0, this vanishes, and y becomes f of x0, which should be the case, right? And then it makes the slope f prime of x0. Any questions? Okay, so I still some folks are submitting the answers for the integral. Well, x over dx, I don't understand why we wrote tangent alpha at x not. Oh, so, well, what it meant was that well, you are measuring the tangent of the angle between the tangent line and the x-axis, right? And you can do it at every point on the curve. So here I'm doing it at point x equals x0. What does the 1 mean? Where is 1? I didn't see the 1. When I think he means prime. Oh, the derivative. So are you familiar? Well, I hope you're familiar with the derivative from single variable calculus. From the you know what derivatives are, right? Of a function of one variable. Zoom in on the graph, yeah. Good. It's something that you're supposed to know from single variable calculus. And so and then, well, we'll look at examples when we do parametric curves, but just let's do some more examples. Like, so you have, if you have a function of single variable, right? Like, you know, maybe graph like this, and you can draw tangent lines at various points. For example, here, the tangent line will be horizontal, right? Because it makes the 0 angle between the x-axis and itself. And then here, tangent lines, they make the positive angle. Here, tangent lines, sorry, like angle between 0 and 2 point. Here they have, here they make this angle, right? So remember, you always count angles counterclockwise, right? So you start from the horizontal line, and then you count it counterclockwise here. So if you remember tangent, tangent alpha is sine alpha divided by cosine alpha, when either sine or cosine are negative, but not at the same time, that tangent will be negative, right? So in this case, tangent will be negative, so derivative is less than 0. So here prime of this x0 is less than 0. Here the derivative is bigger than 0. And here the derivative at this point is equal to 0. And then I hope you remember this theorem from calculus that if you have a derivative, if the point has a local minimum or maximum, then the derivative of that point must be 0, right? And then sort of if the derivative changes from positive to 0 to negative, right? Then it's a maximum, and if it's the other way around, like this, right? Then you have a minimum. So first, the derivative on the left part of this graph is negative, then it's 0. So here it's negative, here it's 0, and then here it's positive. So this will be a minimum. So this is the local maximum. Here's the local minimum. How are you using the tangent alpha in relation to this graph? So the alpha here, so like I said, you measure alpha between the x-axis and the tangent line. So you dial it counterclockwise like that. Well, I mean, you look into my video, right? So it should be like that. So and then so I was commenting on the sign of the derivative. So sign of the derivative. So since derivative is equal to the tangent of that angle, if tangent is bigger than 0, then derivative is bigger than 0, and if it's smaller than 0, then it's smaller than 0. So that was the connection. It's like so tangent is the derivative, so you can just measure the angle and then decide what the derivative is equal to. It's a local minimum, and this is a local maximum. Good. And again, that's something that you guys should know. But so when we switch to parametric equations, the notion of local maximum and minimum will not be too important anymore, right? Because well, what is a maximum? Maximum simply says that the value of the function here is greater or equal than the value of the function around it in some small neighborhood. That's what local means, at some small neighborhood. Also here, if it's a local minimum, then the value of the function at the minimum is less or equal than the value of the function outside. But when you have a parametric curve, it does all these crazy things, and it doesn't really make sense anymore to talk about minimum and maximum. But we can still talk about the tangent line. So she was asking about amplitude. So the term amplitude is used for this oscillatory behavior over here. So that amplitude will be this thing, right? It's the maximal deviation from the condition of equilibrium. That is called an amplitude. Okay. Good. Okay. So now let's try to generalize the idea of tangents to parametric calculus. So let's get back to parametric equations. And tangents. Now, in order to derive the equation for the tangent, we'll still, in parametric form, we will still use the equation for the tangent in the previous form as we just discussed. But sort of let's see how this goes. So first of all, let's give the parametric description of our curve, right? Where t varies between some limits, a and b. And we assume that both functions, x of t and y of t, are differentiable, right? So the x of t and y of t, they differentiable as functions of t. Differentiable on the segment AB. So in other words, derivative exists in every point. So that also implies that they're continuous. Just to simplify the derivation. Although the whole story can be generalized to curves which are piecewise differentiable. Sort of when derivative exists only on some, it may not exist at certain points. Okay. So now I'm just going to quickly write the equation for the tangent before. So before, when we have y was equal to f of x, right? The tangent line was given by the following equation. So it was, y is equal to f prime of x0, x minus x0 plus y0. And so it's a tangent line passing through point x0, y0 on the curve y equals f of x. This is supposed to be, yeah, so yeah, in some textbooks you denote that f of t, sometimes you denoted g of t, but you can just say, you can abuse the notation and just say that x of t is a function itself. Yeah, I think I will be switching, I will be using both, right? So it's okay to use the same function, the same letter for the variable and for the function, because that's what it is. Like there is no need to introduce extra variables like f and g. I hope it won't cause any confusion. Does it sound good? Okay. That's right. So like if you open the book, I think they write x equals f of t and y is equal to g of t. But it's really not a big deal. So we have this derivative guy here. So what's a derivative? And so f prime of x0 is also dy divided by dx, evaluated at x equals x0, right? Then, well, we can use the chain rule, right? So we can write this as dy, but now we need to remember that x and y are both functions of t. So we can write it like this, dy over dt divided by dx over dt. And so mnemonically, you can think of it as if you can cancel out the dt's, and then you get back to dy over dx. Differentiable, yeah, I'm sorry. So guys, am I going too fast, or because some of you are still lagging? Differentiable. Meaning that they have derivatives. If I'm going too fast, please let me know. I don't want to rush through it. So we require differentiability in order to write all this formula. If derivative doesn't exist, right, then anything that follows below it doesn't make any sense. So the function needs to be smooth enough for this to work. Good. So actually, so if I, let me know if I need to slow down a little bit, or so at least I'm trying to ask questions so everybody can catch up. Okay, good. So here's that, or you can also write it as y prime of t divided by x prime of t, and now you evaluate it at some t equals to t0. What is t0? Well, so we know that point x0, y0 belongs to the graph, to the curve, right? Therefore, there should be some value of parameter t when this happens, right? So what t0 is the following. So it's so x0 is equal to x of t0, and y0 is equal to y of t0. Okay. Now, a quick question. The last formula that I wrote, dy over dt divided by dx over dt, does it always make sense? Does it always exist? Or we need to make some comment about it? No, when it does not exist, Julian. Yeah, absolutely, that's right. So there are problems when denominator vanishes, right? So this is provided that dx over dt is not equal to 0. So in terms of the function of one variable, what does this condition mean? What does it translate to? Horizontal tangents. Well, remember it's dx over dt, so it's the rate at which x changes. Vertical tangent, yes, that is right, that is correct indeed. So let's draw it. Well, I think probably the canonical example will be the circle, right? So if you look at the circle, so here, say we're moving on the circle, maybe so this direction, let's say this point, which is 1, 0, is where we want to calculate the tangent. So as we approach this point, the rate of change of x, right, the rate at which x changes, becoming smaller and smaller. And so let's read. So the circle is x equals to cosine t, y is equal to sine t. And then, well, we can calculate the derivatives also, right? So x prime is minus sine t, and y prime is equal to cosine t. So as t approaches 0 or 2 pi here, right? So this point is 1, 0, and it happens when t is equal to 0 or 2 pi, right? As t approaches 0 or 2 pi, x prime, the derivative approaches 0. So for the rate of change of x, right, rate of change becomes smaller and smaller, and exactly at this point 1, 0, it vanishes completely, right? So therefore, the tangent to the circle at this point will become vertical, as you correctly pointed out. Right, and we know that it is expected, right? Because this function, if you try to write the circles, remember what the circle is. The circle is x squared plus y squared equals 1. Now you can solve this equation for y. You can say that, well, y is equal to, let's take the positive branch, which is the upper semicircle. It will be plus square root of 1 minus x squared. Right, and then you know that if you evaluate derivative or at x equals to 1, it will be infinite. Right, so this is expected. Yeah, that is correct. So I wrote here 2 pi. Because remember, we define the circle here when t varies between 0 and 2 pi. Okay, we're good on this. Okay, let's get to parametric stuff. So this works when this derivative is not equal to 0. Okay. So what shall we do when it is equal to 0? Well, in this case, we can calculate the limits as t approaches that point, and then we know that when the derivative is equal to 0, dx over dt is equal to 0, then the tangent will be vertical. But in all other points, it should be okay, right? So, since we know where these points are, we can just explicitly tell. We just look at the dx over dt. We know where it vanishes, which means that at those points, we know for sure the tangent will be vertical. Okay, so does this mean that t cannot be equal to 0, 2 pi, 4 pi, 6 pi, and so on? Well, I mean, it can be equal to it, just the tangent is vertical. So like, again, it's not a bad thing. It's an artifact of our parametrization, right? It's because we define a tangent, right, as a line that has a slope which is equal to the derivative of the function, right? So it's because of this fact here. And then it just happens that when it's vertical, this derivative is infinite. What we should do, we should say that, well, at this point the derivative is infinite and the tangent is vertical. So t can be equal to those points. We just need to say that the tangent is vertical. Yeah. Okay, let's look at an example. Oh, yeah, and also let's calculate the second derivative, which will be you can use it to study concavity properties, right? So let's calculate dy over d2y over dx squared, right? So by definition, second derivative is the derivative of the first derivative, right? And again, we can use the chain rule to represent it in terms of the derivative with respect to parameter t, right? So it's d over dt times dy over dx over dx over dt. And you can substitute for dy over dx the formula that we already had, right? So let's write it in a bit more compact way, right? So it's the so dy over dx is, so it's d over dt y prime of t divided by x prime of t, and then this divided by x prime of t. Okay, now we can use the chain rule. So it's not the chain rule, ratio rule for the numerator, right? So it will look like, first we take a derivative of the numerator, right? So it's y double prime of t times the derivative of the denominator, x prime of t minus y prime of t times x double prime of t divided by the square of the denominator. So I have completed the differentiation of the numerator, and then I just paste in the denominator x prime of t. And then I can simplify it by just moving the denominator of the numerator down. So it will look like this, y double prime. I'm going to suppress t, the argument, to make the formula look a little shorter, over x prime cubed. So now we can see here that the everything, all functions, everything is a function of t now. So if you know the explicit formula of x of t and y of t, you can calculate the second derivative. So we can use this to study concavity properties, like if the curve is concave up or if it's concave down. Good. Oh, you don't hear me? My mic is working, so David, you don't hear. I got you. Okay. So David, maybe you want to reset it or something. If not, you can just try to disconnect and then reconnect back. Yeah. Maybe, yeah, maybe it's more obvious. But I think he was listening to me before that, right? If he complains to me now. Yes. Okay, let's do an example. So say x of t is equal to t squared, y of t is equal to t cubed minus 3t. And so let's see what's going on with this with this graph. Give this a little bit more space here. Well, so let's just try to sketch it, right, and see what's going on. Where the tangent lines are horizontal, vertical, how in general this graph behaves. Well, maybe we can start off with finding the intercept points, like where this graph intersects x and y axes, right? So when x is equal to 0, then t is equal to 0, right? And then when y is equal to 0, so that happens when t is equal to 0, right? So it's t times t squared minus 3 is equal to 0. So it happens at 3 points, right? It happens at t is equal to 0 and t is equal to plus and minus square root 3. Okay. Right. Now, what the so therefore the yeah, and then as well. So here we see that probably the graph has a self-intersection point because of this, right? So if t is equal to plus, so t is equal to plus and minus root 3. Yeah. So let's do it again. So sort of do the backwards. If t is equal to plus and minus root 3, we know that y is equal to 0 and x is equal to plus or minus root 3 squared, which is 3. Right. So 0.30 over here is passed by this curve twice, right? So this should be a self-intersection point. So therefore, this is a self-intersection point. And it happens for two values of parameter t, and that in between, when t is equal to 0, we are at the origin of the coordinate system. So here, at 0, 0, that corresponds to t is equal to 0. Okay. Good. Now let's try to find tangent lines and try to sketch the graph, what's going on with it. So x prime is equal to 2t. Y prime is equal to 3t squared minus 3. Right? And then to find the tangent line, we calculate dy over dx. Right? And that gives us, according to the formula that we have just proven, y prime of t divided by x prime of t. So that's equal to 3t squared minus 3 divided by 2t. We can simplify it a little bit. You can write it as 3/2 t minus 1 over t. Well, that's not really much of a simplification, just a different way to write it. Okay. And then, well, let's find first places where the tangent is horizontal, right? So where dy over dx is equal to 0. Well, it happens when t minus 1 over t is equal to 0, or equivalently, t squared is equal to 1, which amounts to having t is equal to plus and minus 1. Right? So plus and minus 1 is between, yeah, so 1 is between 0 and square root 3, and minus 1 is between negative root 3 and 0. So the curve will have, the tangent of the curve will be horizontal between t equals 0 and t equals 3, at t equals square root 3, and t equals minus square root 3, right? So somehow in this area here in the middle, it will have horizontal tangents. Okay, and now let's try to find a place where the tangent will be vertical. So this is horizontal tangent. This is the condition. And then vertical tangent. What is the condition for the vertical tangent? We just talked about it. Does anybody remember? What has to happen with the function? Yeah, that's right. dx over t is equal to 0. So x prime is equal to 0, or 2t is equal to 0. So therefore, t is equal to 0. So at t is equal to 0, tangent is vertical. Which means what? Which means that so here, tangent is vertical, because t equals to 0 corresponds to 0.00. Then at t equals 1, tangent is horizontal. Let's also now t equals plus minus 1, tangents are horizontal. And let's also find tangents at t is equal to plus minus square root 3. So what happens around the point of 0.3 equals to 0? Okay, so when t is equal to plus root 3, right? We have dy over dx is equal to 3/2 root 3 minus 1 over root 3. Right, so we know that square root 3 is approximately 1.7. It's bigger than 1, right? So we're not going to evaluate this number. We just need to know that this is bigger than 0. And when t is equal to minus root 3, dy over dx is equal to 3/2. Well, minus the previous one, right? So minus root 3 plus 1 over root 3, and this is negative. So how do you think the graph will look like? Can you describe it I'm not sure what the discussion is about, guys. Limit, well, we're not, no. So the exponential, yeah, that's right. So it's, yeah, so what Alex is saying is correct. So when x in your formula is an integer, right, it's the limit of that sequence. Yeah. But here it's just the function t minus 1 over t. We didn't do any limits. So can you sketch, like, can you describe how the graph will look like? What do you think? Given what we know now. So we know that the tangent at t equals minus root 3 will be negative, at plus root 3 it will be positive. So, and then somewhere in between, it will be 0. Why are we evaluating it root 3 again? I'm a little lost. Sure. So the reason why square root 3 is special is because when t is equal to plus or minus root 3, we know that we are at the same point, right? It's the point x equals 3, y equals 0. So it's this guy over here. It's a special point in the curve where the curve self-intersects. So expect to have a loop like that, so it with a self-intersection. Sarah, does that make sense? Yeah, Clarice, it's not, half of infinity sign, yes. You are correct. So I think what Clarice is alluding to is if we actually try to draw it, it would look like this, right? So it's like that. Let me try to make it thicker. Thicker. Let's see that it's right. So we just evaluated the value of the tangent. So when and then we move along the curve like this. So first we arrive to this point at value t is equal to minus square root 3. And then we keep traveling upwards until we reach this point t equals minus 1, where the tangent is horizontal. T equals minus 1. Then we approach t equals 0 when the tangent is vertical, and then it's kind of symmetrically replicates back, right? So then we come here, t is equal to 1. Again, it's horizontal, as we have found. And then we come back again to the self-intersection point at value t is equal to plus square root 3. And we shoot off to plus infinity. Why can't the graph travel the other way around? Well, because it's not the way the function works, right? So if you take literally this formula and say that t varies between minus infinity and plus infinity, well, there's no equal sign. So you come from negative values to positive values, then that's what happens, right? So because you see here, good question. So we know when t is equal to negative root 3, right? So well, let's draw it here. So this is t 0. These are the most interesting points in our story, right? Where we studying the I guess FAD. I'll answer question in a second. Right. So and then parameter t evolves in this direction. So first we come to minus root 3, then minus 1, and so on. So we know that when t is equal to minus square root 3, the tangent is negative. The derivative is negative, so this angle is negative. Yeah. So and then when t is equal to plus root 3, it's positive. So it actually has to go like this. Yeah, we'll talk about concavity in a second, right? So Sharon, does it answer a question? Good. Now, Fad, he privately asked me, why can't it be a parabola? Well, it's a good question. However, notice here that we have y is equal to t cubed, right? So it's a cubic thing. So it's a curve which has square and the cube in two different equations. So to get a parabola, you need to have one equation linear, the other equation quadratic. And this is not the case here. This is not the case here. It's a cubic. Yeah. So as you can see, there is no particular good presentation of y in terms of x or x in terms of y. Okay. Now, Quad is asking about concavity. Let's talk about that. Let's calculate the second derivative. So, well, we can either take out the formula from which I derived for you in general in terms of x prime and y prime, or we can just, so we can either take this, but this may be a bit longer. So we can, let's work with this formula, because we know exactly what dy over dx is, right? So the dy over dx is this. So what we need to do, we need to take another derivative of that and then divide by x prime. This way, I think it will be a bit faster. Okay. So, yeah, so dy over dx squared. Let me write it again. So it's d over dt, dy over dx, divided by dx over dt. And dy over dx is 3/2 t minus 1 over t, everything prime, divided by x prime, which is 2t. And so what is the derivative for that? It's 3/2 times 1 plus 1 over t squared, right? And divided by 2t. Or we can brush it up a little bit. This will be 3/4 t squared plus 1 divided by t cubed. Okay. Right. And then, well, let's, can you tell me where, for which values of t, the second derivative is positive, and for which values is it negative? Positive, for t equals, that's right, so for t bigger than 0, it's positive, for t less than 0, it's negative. Yes, that's right. Indeed, so the sign definition is comes from this factor, because t squared plus 1 is an even function, so therefore the sign definiteness of t is of the whole thing is determined by the denominator. And indeed, let's check, right? So the branch of the function, I think this graph is just too dense. Let me just draw. Sorry, there's some, my neighbors, they always vacuum their cars when they give talks and lectures, which is so annoying. Yeah, otherwise we live in a great neighborhood. Okay. So I'm just going to draw it again. I think it was green. Right, so the branch when t was less than 0. Different color. So this branch is t less than 0. And this branch is when t bigger than 0. And that's consistent with what we know, right? So this is concave up, and this is concave down. Okay, any questions? Good. So let's maybe make here a 3-minute break, or maybe 2-minute break. I'll be back, and then we'll continue. Okay. So I'll see you in a second. Hey, welcome. Oh, I'm back. I see there's some discussion about Piazza. So I believe there's a quick. So I never personally used Piazza, but if you want, we can start the site. Okay, so let's see. I think that Lily would become from the professor. She's asking questions about stuff. So I never used Piazza. So can somebody maybe unmute themselves and explain how this works? Like, do I need to set up the website, or you guys can invite everybody, or how does it work? Rohan or Sheila? I'm happy to assist that.
My mic works, but I don't know how to set it up. I'm sure, it's pretty self-explanatory on the website. But I think you might need to make it. So
I can do it if you guys want it. I can do that. Yeah, sure. So basically, so Piazza is just it facilitates discussions between students and faculty, right? So like you can post a question and somebody answer it. Is that right?
Yeah.
Okay. Because on the B courses also has this option. There's like discussions in B courses. Maybe it's less flexible than Piazza. Discussion from that's right. As Amak is saying, I can do Piazza. That's fine. Yeah, I'll look into it today and I can set it up. Yeah.
Thank you.
Sure. I see. Did I answer all the questions? What we don't get and the prof answer, but yeah, okay. But yeah, but of course, like we also have office hours. Okay, now there's a private question from Sharon. Just for clarification, t equals minus square root 3. Does it also count as the point where t is equals square root 3? Is it also positive? No. So that's why I'm saying the self-intersection point, it just happens that this point occurs twice, right? So it happens, the curve passes through this point twice. But you should actually think of it as a different point of the parametric curve. So that's why, you know, this branch, this branch is when t is less than 0, the other branch is when t is bigger than 0. So we should t serve with square root 3 to be on the graph. Oh, okay, good. So t, what's good? So well, okay, so let's get back to the previous graphing thing. It's at the same point. So the point 3, 0, so this point 3, 0, the self-intersection point corresponds to both positive root 3 and negative root 3. I'm sorry if the graph is too busy, but well, let's draw it one more time. So goes like this. Now, and you travel like that, right? So when t goes from minus infinity to plus infinity, you go like this. So first you get to this point when t is equal to minus root 3. Then you get to the top, it's minus 1. Then you get here, we have 0. You get to the bottom, it's 1. And you come back again, it's plus root 3. I hope this should be okay. Good. Okay. So did you guys find out the question about integral dx over dx? Well, the answer is, in fact, there is no surprise, and the answer is equal to, no, it's not definitive, it's a definite, no, it's 1 over d log of absolute value of x plus a constant. Well, too bad that you guys are muted. I hope some of you, at least some of you are laughing out loud, right? So yeah, of course. Right, so the catch was the d on top and d on the bottom, they look a bit different. Yeah. So if you type it in LaTeX, probably dx on the top will be close together and then d in the bottom will be separated. I'm not getting the joke. Okay, I'm getting back. So look at the answer. So do you know what d, okay. Yeah, that's right. So Julian explained 1 over d is a constant. And integral over dx over x is a logarithm. Well, it's a, you know, it's a convention. So most of the books, like okay, all research papers that you see, they almost all write log as log, right? So that means natural log. So it's log base e. Some books use notation ln, but it's less common. I think like depending on like which country you're from, like so where I grew up, so like we mostly used ln, but I think sort of more of kind of North American convention is to write log. Right. In sense, all logarithms are the same, right? So there is a base conversion formula. Okay, now let's look at another example of, okay, we actually need to switch to, so the way this app works is like I have a big sheet of, well, stuff, and then I just move around it. So once I'm done, I'll send it to you, I'll attach it to the D courses. Yeah, we got to. Okay. So next example is called cycloid. Cycloid curve. Some of you prefer line. Okay. Well, it's a matter of taste. So to fully draw a graph, we need to find one all x-intercepts, two horizontal vertical tangent. So good. So Jonathan, what we did was a complete, well, not complete, was like a very detailed analysis. We just did it, to practice the skills that we just developed to calculating the derivatives and tangents. If you have a gut feeling how the curve should look like, you can just sketch it, right, and explain why this is the case. What we did right now, it's maybe a little bit an overkill. But yeah, like in principle, that's what you would do if you don't understand what's going on. Yeah. Of course, like, as you gain experience with those things, you will need less and less of preparation. When the graph parametric curves, when we graph parametric curves, do you want us to add arrows? No, you don't have to. No, you don't have to. Just for explanatory purposes. Cycloid. So what is a cycloid? It's actually, it appears in everybody's daily life. So say you want to drive somewhere, you sit in your car, right? So this is the tire of your car, and then you make a hash mark with a chalk, right? So you mark with a chalk, maybe at the bottom of the tire, right? And then you start driving. Well, mathematically, we have a circle, right, that rolls on a horizontal plane, and you are tracing the position of one point on that circle. So like the chalk mark on the tire, you're asking yourself, how will it travel in space as you drive your car? You probably know that in some cities, like policemen, when you park a car and then there's a limited time for the parking, they would mark it with a chalk, right? And yeah, so you can see the chalk mark on the back of the tire. Yeah, so basically, as it starts rolling, it will make some. They vandalize our tires. Yeah, exactly. So like they would have a big stick, with a big chalk on the top, and they would mark it. Yeah, I don't like it either. Well, so it's clear, right? So like when it's on the bottom, well, sometimes this hash mark will be on the bottom, and then it rises, then it's somewhere halfway through. It will be here, right? And then as you keep traveling a little bit further, it will go on top, right? And then it will start descending down. So it will make this kind of smooth arch. At least, well, it may not be smooth at the bottom, but we'll figure it out, right? So if you try to connect the dots, it would look somehow like this. And then it starts over again, right? Because the process is periodic. If you drive forward a few feet and then back, it usually raises the chalk. Well, is that true? Okay, I didn't know. I would imagine you have to drive for a while to make it right. But if I were them, I would make the chalk mark on the side of the tire. That would make things harder to raise. Yeah. So our task is to find this curve, right? So find the parametric equation. Find the parametric equation for cycloid. Parametric. For this red curve. Yeah, and then we'll say anything we can say about it. We'll calculate, find tangent lines, but then we'll introduce the area, the curve length, and we'll beat this curve to death. Yeah, it's a good exercise. Now, as a homework, and maybe we'll do it for the discussion, you can sort of find the modification of this problem. Now, assuming that you're actually in circles and then you're riding on the inside of a big circle, right? So it's kind of a modification. And then it's basically the same question, only that you ride, here's your chalk mark, and you're riding like that. So it would do something like this. And you can do either this, or you can ride on the outer side. Okay, maybe it's a good problem for the discussion. On the outer side, and then again it will look to make shape like that. It's kind of the circular version, but that will be for later. Yeah. So let's try to find this equation. So to do that, we need to make a slightly bigger picture of the wheel. So let's say it rolled a little bit. And so say we pick the coordinates in such a way that when the mark was at the bottom, right? So here we start our travel from the point 0, 0, and that's where the mark was. And then as the tire rolls, that's that's too high. I'm sorry. Somehow like that. So as the tire rolls to the right, this mark rises, and then at some point in time, where the bottom of the tire is here, let's call this point T. This point is P. So the mark is at point P. This is point O, the origin, and well, this is actually the bottom. Try to make it better. The bottom of the wheel is here. Right, so let's say your tire has radius R, which is what, 22 inches, I don't remember. And same as here. So this is also R. Say this point C here is the coordinates of the center of the wheel. Towards the top of the screen, I'm sure it's in blue. This, or it's a modification of the problem. So let me try to rewrite it. Modification. So it's a follow-up problem, which we'll talk about later. Yeah. Okay. So now our task is to describe the coordinates of point P. Right. And we'll do it in terms of the angle theta. So if this angle theta, so let's say the wheel rotated by angle theta, right? So we're assuming that there is no sliding, right? So the wheel actually travels without sliding, and because of that, the length of the OT, right, length of the segment OT is equal to the length of the chord, excuse me, not the chord, of the arc, of the arc PT. Meaning no friction. No, there is friction, right? If there will be no friction, you won't be able to roll, right? So that's why we can drive cars, because there is friction. There is no sliding. Like say, when you drive on the slippery road, sometimes sometimes the wheel spins, but there's no traction with the asphalt, with the pavement, and it would just spin and spin. Does that make sense? Okay, and what is this length equal to? If the radius is equal to r and the angle by which it rotated is theta. So I mean, Sheila, so the reason why I'm saying is because it's to quantify the statement that OT, so this distance from O to T is equal to the arc length of arc length from P to T. Okay, we'll get back to this in a second. So what is the difference? What is the distance in terms of R and T? R times theta, of course, it's R times theta. If theta is measured in radians, that's what the distance will be. So this is R theta. Okay, so now you can find the x coordinate of P. So let's call it, how do you call it? Yeah, let's just call it x. Little x and little y. So to find x, we need to subtract. There's a simple geometry here. Let's call this point maybe Q. There's a straight angle here. Now the x coordinate should be equal to OT minus PQ. Why is the arc length R times theta? Well, that's what the definition of the radian is, right? So if you have a circle, right, of radius r, and you are looking at the arc of angle theta, then its length is equal to r times theta. That's the definition of the radian. So the full circle is 2 pi radians. And the circumference of the circle, so the length of the perimeter of the circle, is radius multiplied by 2 pi. Good. Yeah. I hope everybody okay with the formula with x. So that is equal to r times theta. And PQ, we can find it from this right triangle. What is PQ equal to? R times sine theta, that's right, yes. R minus R times sine theta. Right, in this right triangle, it's the opposite side. Right? We can take R outside of the outside of the parentheses, so you get R times theta, so that's x, right? And then now let's find y. We just copy it here for so x is equal to R theta minus sine theta. So see, not so often we have angle and the trigonometric function of that angle independently in the same formula. But here this is the case. And y here, it will be CT minus CQ. So CT is of course the radius, and CQ will be the other function, right? So it's minus radius times cosine theta. So that gives us R times 1 minus cosine theta. Here we are. Now, if you want to describe the whole motion of the car, assuming that it can move forward and backward, then we should allow theta to vary between minus infinity and plus infinity. to make it really kind of to make the curve stretch from left to right and backwards. So this is the famous cycloid curve. Okay, now let's find its let's study its differentiability. What happens when we'll find slopes, we'll find tangent lines. We'll try to say as much as possible we can about it, about this curve. Actually, I think for the purposes, well, we wasn't just copy this formula, so I don't have to go up and down again. So x is equal to r times theta minus sine theta, and y is equal to r1 minus cosine theta. So here, r is a constant, right? It doesn't change. Well, unless the pressure of your tires drops, the radius does not change. Okay, so let's find the slope. I got, well, let's move it, I'm sorry. Where's my, okay, so tangent lines. And so we need to calculate the derivative dy over dx, which as we know is so now the role of time, right? So let's assume that the car is moving with a constant speed, right? Then again, sort of because there's no sliding, right? So because the wheel does not slide, the speed of the car translates directly into how fast the wheel is rotating around its axis. So therefore, we can think of theta as the parameter that counts time, right? So as theta changes, the time goes. So in other words, the role of parameter t here will be played by theta. So this is the parameter. This is the these two equations parameterize curve as a function of theta now. So theta is the parameter. And we will calculate derivatives with respect to theta now. dy over d theta, dx over d theta. Okay, so it's equal to r1 plus cosine theta divided by minus, right, divided by y, sorry, yeah, it's getting y first, right? So it's r times, yes, it's r times sine theta, and because derivative of cosine is minus sine, and there's a minus, divided by x prime, which is r times 1 minus cosine theta. So r cancel, that gives us sine theta divided by 1 minus cosine theta. Okay, so the let's see. Well, we kind of know how this thing looks like, so we can just find. We expect that there will be maxima and there will be spikes, right? So the curve is not going to be smooth everywhere. That's how it should look like. Right, so we expect to have points where the tangent will be horizontal, right? Let's say this is point is 0, 0, where we start moving. So there will be points where the tangent is horizontal, and there will be points where it may be infinite, right? So when it sort of spike when it goes like this, but we need to figure out what's going on as we approach this, when we approach the bottom of the curve. Okay, so when tangents are horizontal. When the derivative is 0, right? And then simply means that it's when sine theta is equal to 0, right? The denominator is well defined, so it's simply so theta is equal to pi k, right? Where k is an integer. So if you know z, this font is denotes the set of integers. So these are numbers like -3, -2, -1, 0, 1, 2, 3, etc. And because x is equal to r, so x is equal to r times. So now we can find out at which values of x it happens. There's like x1, x2, and so on. So these are the points when xi or xk, right, is equal to r, which is a constant, times pi k, right? Times pi times k. So that's when the hash mark is at the top point, right? And this is expected, right? Because you see, the wheel makes a full revolution when we go from here to here, like this. And since it's symmetric, it's expected that the maximum will be in the middle, right? And we know how long this thing is, right? So if this is 0, this is 2 pi times r. So the wheel will completely make the full turn, so that this red point will make full revolution from bottom position back to the bottom position, which means that the car will have moved by 2 pi times r. In fact, you probably know that's how when your car has an odometer, right, you should not trust the odometer literally, right? Because it assumes that you are driving at the manual pressure. So your cars are inflated to the pressure according to the manual, and then there's no there's no sliding. So basically, what happened here? So if by one revolution the car moves by 2 pi r, right, that information is used in the odometer calculation. So for example, if you underinflate your tires or overinflate them, then your odometer is not going to tell you the truth, right? Especially it matters in older cars. As you can imagine, with years, it may lead to some discrepancy. Okay. I think in modern cars, there's sort of like two indicators that basically the one information comes from the engine, the other from the wheel. Okay, yeah. So these are, and then so these are the y's, and then y's of course are equal to 2r. Right. So these are the tops, twice the radius. All these points are twice the radius. Okay, and now let's see what happens at points when, what happens as theta approaches 0, right, or pi n. So if you have vertical tangent lines. Well, here it's a bit more tricky because, well, so the derivative x prime dx over d theta is equals to 0 means that 1 minus cosine theta is equal to 0. So cosine theta equals to 1, right? But cosine theta is equals to 1 at the same time when sine theta is equal to 0. So as theta approaches 0 or 2 pi or 4 pi, we have an indeterminate expression. So we need to use L'Hopital rule. I'm not sure what it says when you wrote y something equals to r. Oh, sorry. It's the k. So these are y sub k. So these two formulae, they show the position of points when the tangent lines are horizontal. Yeah. Why are we evaluating it like a limit? Well, because as you send theta to 0 or to 2 pi, right, so this expression here, so limit as theta goes to 0 of sine theta over 1 minus cosine theta is not directly, you cannot evaluate this directly. Is that gamma or r in the x equation? We don't have gamma. Where is gamma? We only have little r. Dana was that, yeah, the first one. Okay. So yeah. So we need to use L'Hopital rule. You know the joke about L'Hopital rule. The hardest part of the L'Hopital rule is to know which letters in L'Hopital are pronounced. Well, of course, unless you take French class, then of course you know. Yeah. So what's the L'Hopital rule? We take a derivative of the numerator and the denominator, and then we evaluate it, right? So it's the limit as theta approaches 0. So in this case, we're sort of asking what's going on if we try to study the motion of the car just before in the very beginning. But of course, you can just periodically continue to the left, so it doesn't really matter. Instead of 0, you can put 2 pi or 4 pi or any integral number of pi's. So say theta approaches 0, derivative is cosine theta divided by sine theta. And this is equal to what? Yeah, Julian, I'll answer a question in a second. What is this limit equal to? Infinity, of course, yeah. So this is equal to infinity, which is exactly what we need, right? So, so remember, so this computation was for the derivative. So it's the limit as d as, so that was limit of the derivative as theta approaches, well, 0 in this case, so it's equal to infinity. So therefore, we know for sure that this tangent lines will be vertical at those points. So tangent lines are horizontal at theta equals pi k, and then for completeness, tangent lines are vertical. At theta is equal to 2 pi times maybe another integer L, right? Where L is an integer. Oh, Jonathan is replying to Julian, right? So the 2r comes because, you know, if you have a wheel of radius r, circle of radius r, and it stands on the bottom, like on the plane, then the top has height 2r, right? There's a whole diameter work. Yeah. That's right. What does the I represent? L isn't, so L represents, because, you know, it's a periodic process. So this is 2 pi r, so this is 2 pi times r. Yeah, theta is equal to 2 pi. So, right, it represents an integer. So for every integer, L, say 100 or 99, right? If your car drives that far, the tangent line will be vertical. So tangent line becomes vertical every time the theta, every time the wheel completes the full revolution. which means, well, that just means the theta belongs to the set. So theta is 2 pi, 4 pi, 6 pi, etc. Can k be even, or does it have to be odd? So k above can be any integer. It doesn't have to be even or odd, right? Because sign vanishes for pi times any integer. So both k and l can be any integers, no matter the parity. David says he's confused about taking the limit. Well, so here's the answer for the derivative. Try to evaluate it when theta is equal to 0 or 2 pi. Then we'll get in trouble. So you have to take the limit. Yeah. So what we have found here is that this is it's a continuous function, right? But it's differentiable everywhere except those points here, because the derivative becomes infinite. A kind of unrelated question, but when will the office hours be posted? It's a cusp too, yeah. So so I think office hours will be sometime on Friday. So like on Friday we'll have a discussion in each of the sections, and then so those who cannot attend the 10 a.m. class can join later, and then I'll announce. So I don't know yet, but I think I'll figure it out later today. So there will be main window for office hours, and then if you cannot make that window, then you can join. You can send me a message, and I'll find another time for you. Yeah. Yeah. So these are cusps. You can also these are cusps. Also, interesting thing that the sign of the discontinuity changes. So as we approach, say here, the tangent line sort of it goes down, 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 and then as you approach from the left, every cusp, then the derivative is equal to negative infinity, right? And as you approach the cusp from the right, the derivative becomes it's a positive infinity. So at those cusps, the derivative switches from negative infinity to positive infinity. Okay. Oh, we're already out of time. Somehow I planned to speak a bit more today, but I think it's good that we move with the space and I'm answering all the questions. Yeah, so we don't have. I want to talk about areas, but well, we shouldn't do it probably now. Yeah, so we'll start with this next time. Yeah, we'll do areas, we'll do polar coordinates, arc lengths, and the rest of this stuff from 10.2 and 10.3 and 10.4. Any other questions about anything we had discussed today? Shouldn't be xk to be 2 pi ik plus pi. Well, so xc here, there's a sign, right? So when you evaluate sine theta, when theta is equal to pi k, you get 0. Right. Can you scroll up? Yeah, sure. Cycloid curve examples when you are doing other. Yeah, so like we'll talk about polar coordinates next. So it will be easier to answer this in terms of polar coordinates. So you have a big circle of radius big R, right? And then there's a wheel with a circle with a radius small r, and it sort of rolls. It rolls inside. Good. Okay. I think yeah. Good. So that's it for today. See you guys tomorrow. Thanks. Bye.